Good morning. This is Dr. R.K.Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain forced convection heat transfer for plug flow in circular tube under constant wall heat flux in thermally fully developed region. So the problem statement is you have here a very thick slurry is flowing in a circular tube of radius r. Since it flows nearly as a solid plug, the velocity profile is approximately flat over the pipe cross section. Bz equal to V may be assumed constant. For Z less than or equal to 0, the fluid temperature is uniform at the inlet temperature T1. Means this fluid is just about to enter the tube. For Z greater than or equal to 0, heat is added at uniform constant radial flux Q0 through the tube wall. Axial heat conduction and viscous dissipation effect may be neglected. Thermal conductivity K and thermal diffusivity alpha may be assumed constant. So this is problem statement. Now this is a schematic here. So here you have a tube. Inside of tube you have a fluid of the slurry in plug flow mode. So here you have constant velocity across the cross section here, the flat velocity profile. So absolutely plug flow. Now at the wall here you are maintaining constant heat flux somehow by means of some heating coil something. So Q0 is flux which is constant over the entire length. So this flux will be entered to the fluid. Now fluid is entering at a temperature T1 at the inlet here. So this also have a flat temperature here. As the fluid will pass through it, it will start gaining the heat from the wall at Q0 flux and it will raise its temperature here. Now applying the energy of change for Newtonian fluid in cylindrical coordinates. So this is energy change equations. Rho Cp cap del T upon del T plus Br del T upon del R del V theta upon del R del T upon del theta plus Vz del T upon del Z equal to K 1 upon R del upon del R del T upon del R plus 1 upon R square del square T upon del theta square plus del square T upon del Z square plus mu 5V. So this is energy equation. Now we will put the limitations or boundary conditions or constraint we have. First we want to solve it for steady state operation. So this time derivative would be 0. Only flow in axial directions, purely axial directions here. So radial velocity and theta velocity components are 0. So Vr and V theta are 0. Now from here, so we are considering here axis symmetric, so nothing should change with respect to theta 2. So this term is also 0. Then no conduction in z direction, so we are considering this del T upon del Z is also equal to 0. So by putting all these constants here, and again we are considering the viscous dissipation term is also equal to 0. Negligible as compared to this convection term. So for that case, the conduction term here, so you have rho Cp cap Bz del T upon del Z equal to K 1 upon R del upon del R del T upon del R. So this is main equation which need to be solved. Your boundary conditions for this are at R equal to 0, T equal to finite, R equal to R, that at the wall of the tube you are maintaining constant flux minus K dt upon dr. Your conduction flux should be equal to the flux maintained at the wall, that minus Q0. Z equal to 0, that your T equal to T1, that is the means temperature of the fluid at the entrance. In non-dimensional term, similarly as we did for force convection case, so here you have theta equal to T minus T1 upon Q naught R upon K, then epsilon R upon R, eta is non-dimensional distance is consider eta, that Z upon rho Cp cap Bz max R square upon R. Now from here we can calculate del theta upon del T is 1 upon Q naught R upon K. Then you have del eta upon del Z is 1 upon Cp cap Bz max R square upon K. Now we can substitute everything back. So from here we have del theta upon del eta equal to rho Cp cap Bz max R square upon K upon Q naught R upon K into dt upon dz. Now from here we can get the expression of dt upon del t upon del z equal to Q naught R upon K upon rho Cp cap Bz max R square upon K del theta upon del eta. So from here you have expression of del epsilon also, that 1 upon R del R. So we have this. So now we will get from equation 2 and 5 del theta upon del epsilon is equal to 1 upon Q naught R upon K into del T upon 1 upon R del R. Now del T upon del R is equal to Q naught upon K del theta upon del epsilon. So from here you can end up here with this, you are multiplying this R del T upon del R Q naught upon K del theta upon del psi. Now differentiating this with respect to R, so you will get this Q naught R upon R K del upon del epsilon, epsilon del theta upon del epsilon. Now multiplying this term by 1 upon R, so you will get 1 upon epsilon R, Q naught upon R, del upon del epsilon, epsilon del theta upon del epsilon. Now from equation 1, 4 and 6, we will get this equation, that rho Cp cap Bz max Q naught R upon K, rho Cp cap Bz max R square upon K del theta upon del eta equal to K 1 upon epsilon R, Q naught upon R del upon del epsilon, epsilon del theta upon del epsilon. So by simplification of that, we are ending up del theta upon del eta is equal to here 1 upon epsilon del upon del epsilon, epsilon del theta upon del epsilon. So this is equation which is need to be solved. For that, boundary conditions are at epsilon equal to 0, R equal to 0, theta equal to T minus T1, Q naught R upon K equal to finite. At R equal to R, epsilon is 1, so del theta upon del epsilon is equal to K upon Q naught del T upon del R. From here this you will get equal to 1. Then eta equal to 0, T equal to T1, so your theta equal to 0. So these are your non-dimensionalized boundary conditions. Now for large eta, after the fluid is sufficiently far downstream from the beginning of heated section, it is expected that constant heat flux through the wall will result in a rise of fluid temperature that is linear in eta. It is also expected that the shape of temperature profile as a function of epsilon will ultimately not undergo any further change with increasing eta. Therefore, asymptotic solution would be theta equal to C naught eta plus psi is a function of epsilon. Now this is not complete solution because it doesn't satisfy your boundary condition 3. Now boundary condition 3 is again being transformed into a integral conditions here. So here we have just taken here this case that at z equal to 0 the fluid is entering at a uniform temperature T1. So in this particular, if you are reference temperature you are considering T1, so here it means it's not gaining any energy here, so no energy is entering here. Now from z equal to 0 to z, fluid is getting heated by this constant flux maintained at the wall by means of some heating coil. So you are getting this much energy in 2 pi Rz Qz. Now this much energy is being taken by the fluid from here, that rho Cp cap T minus T1 Bz R into dr. So this much energy would leave from here. So what this, the leaving energy is same, the whatever is gaining. So this is what is being given here as an integral boundary condition here. So now we can non-dimensionalize this boundary condition 4. So you have at epsilon is r upon r. You get expression of r here, then theta equal to t minus t1 q naught r upon k equal t minus t1 theta q naught r upon k. Vz equal to Vz max equal to V only. So this is actually, you have plug flow here. So you can substitute all of them back into boundary condition 4. So you will get 2 pi r z q naught equal to 2 pi 0 to 1 rho Cp cap theta q naught r upon k Vz max epsilon r minus r d epsilon. So from here you will get z upon rho Cp cap Bz max r square upon k equal to 0 to 1 theta epsilon d epsilon. So this is the expression of eta actually. So eta equal to 0 to 1 theta epsilon d epsilon. This is equation number 9. This says that energy entering through the wall over a distance eta is the same as the difference between energy leaving through the cross section at eta and energy entering at eta equal to 0. From equation number 8 you have theta equal to C naught eta plus psi. So now from here we can find del theta upon del eta equal to C naught and del theta upon del psi equal to del psi upon del epsilon. So from equation 7 and 10 we can calculate the C naught equal to 1 upon epsilon del upon del epsilon epsilon del psi upon del psi. Since psi is the function of epsilon only, so for that we can convert this partial derivative into total derivative. So for that case you will get C naught equal to 1 upon epsilon d upon d epsilon into epsilon d psi upon d epsilon. Now we can integrate that. So if we integrate that we will get d epsilon upon d psi upon d epsilon equal to C naught epsilon by 2 plus C1 upon epsilon. Again integrating it, you will get psi equal to C0 epsilon square upon 4 C1 ln epsilon plus C2. Now we have boundary condition 1 and equation number 2. At epsilon equal to 0, we want t minus t1 q naught r upon k is a finite value. So but from here this will make it infinite ln epsilon terms. So therefore the C1 is forced to be 0 to make it finite. So your C1 is 0. Now psi equal to C0 epsilon square upon 4 plus C2. Now theta equal to C naught eta plus psi. Now we can substitute the expression of psi. So theta equal to C naught eta plus C naught eta square by 4 plus C2. Now we can find del eta upon del psi equal to 2 C naught epsilon upon 4. Now boundary condition 2, epsilon equal to 1, del theta upon del epsilon equal to 1. So we can substitute 1 here, we can calculate your constant C naught. So C naught equal to 2. Now we will get expression of theta. So theta is 2 eta plus 2 epsilon square upon 4 plus C2. So your theta is this one. Now equation 14, and now we want to have boundary condition 4 from equation number 9. So what we have there, so this is your boundary condition 4, eta equal to 0 to 1, theta epsilon into d epsilon. Substitute here expression of theta. So theta is 2 eta plus epsilon square by 2 plus C2, multiply by epsilon into d epsilon, multiply inside and integrate. So if you multiply and integrate it, you will get 2 eta epsilon square upon 2 plus epsilon 4 upon 8 plus C2 epsilon square upon 2, and limit is 0 to 1. So if you substitute here, you will get C2 equal to minus 1 upon 4. Now from equation 14, you will get 15, sorry. So you will get theta equal to 2 eta plus epsilon square upon 2 minus 1 by 4. It is exact in limit as eta tends to infinity. For eta greater than 0.1, it predicts the local value of theta is to within about 2%. Arithmetic average temperature over the cross sections. So this T here, so you have, this is the expression for that, TR dr d phi divided by area. So you have expression of theta. Theta is 2 eta plus epsilon square upon 2 minus 1 by 4. The substitute the expression of theta is t minus t1 upon q naught upon r. So you will get expression of t is this one. Now we can have this expression can be substituted here, multiply r dr into d phi. So this r is here, epsilon r, then you have r multiplied by d epsilon. So this is expression of dr, and d phi is 2 pi, and epsilon is changing from 0 to r, and in denominator you have pi r square. So multiply it inside and integrate it. So if you multiply it, you will get this, and after integration of this one, you will get t1 epsilon square upon 2 plus eta epsilon square upon 2 plus epsilon 4 upon 8 minus epsilon square upon 8 bracket close q naught r upon k 0 to 1. Substitute the limit here, so you will get t actually arithmetic average temperature equal to that T1 plus 2 eta q naught upon R. Now bulk temperature TB, it is temperature one would obtain the tube was choked off at Z, and if fluid issuing forth were collected in a container and thoroughly mixed. This average temperature is sometimes referred to as cup mixing temperature or flow average temperature. So you have here T bulk temperature expression Vz into T upon Vz average. So here you have Vz into T R dr d phi upon this volumetric flow rate Vz R dr d phi. So substitute the expression of T. So this is expression of T Vz max T1 2 eta plus epsilon square minus 1 by 4 q naught by r epsilon or r is r and dr is r d epsilon, and d phi is 2 pi, and this 0 to r will be changed to 0 to 1. In denominator you have this Vz max r into dr, so Vz is not a function of r here because this is a plug flow region. So here you can integrate that here, so if you will integrate that, you will get this expression here that Tb equal to T1 plus 2 eta q naught r upon k. Now from equation 17 we have wall temperature, that Tw equal to T1 2 eta plus 1 by 4 q naught upon r. So we have equation 20 wall temperature minus bulk temperature. So you have this one here 1 upon 4 q naught r upon k, thus the 1 by 8 q d upon k. Now conduction flux equal to convection flux, so conduction flux is q naught h Tw minus this, so you have Tw expression from here. Substitute here from this, so you have hd upon k equal to 8 equal to Nusselt number for plug flow under forced convection in circular tube. So the reference for this is transport phenomena by Ward, Stewart and Lightfoot. So in case of suggestions and any comments, you can drop your comments, and we will try to improve it. Thank you very much.